Now we'll see about part B of Module 3, which is covering Biotsavarts law and its applications. Next, Amperes law and its applications, Stokes theorem, curl properties and formulas, scalar and vector magnetic potential. Right? So this is about actually static magnetic fields. This is also called as a magnetostatics. That means when the magnetic field is at stationary, then that is called as a magnetostatics. So to discuss about magnetostatics, first we should know what is meant by DC current, next current density, next magnetic flux density and magnetic field intensity, and what is the relation between magnetic flux density and magnetic field intensity. We know that the current flowing through any conductor is nothing but rate of change of charge, I is equal to dq by dt. Next, current density is nothing but current flowing through the element per unit surface area. So J is equal to I by S. This can be explained by taking one simple example. That is nothing but, consider this is the conductor having the surface area S, right, through which the current is I. So the density, current density of this conductor J is equal to I divided by S. I unit is ampere and S unit is meter square. So J is equal to I by S. Now consider differential surface area ds through which the current is di. Then for this element, the current density J is equal to di divided by ds. That is current divided by area. Now di is equal to J into ds. Take the integration both sides, therefore I is equal to surface integration of J bar dot ds. I is equal to surface integration of J bar dot ds. This formula is very useful for solving the problems also. Now let's see the same thing here. This is a conductor. Consider the differential surface area ds through which the current is I di. So therefore J is equal to di by ds, di is equal to J ds, I is equal to surface integration of J bar dot ds. Next we are going to define one more important definition, that is about magnetic flux. So let's see here. To define the magnetic flux, first we can consider the first magnet. So for the magnet, right, so once suppose if this side is emitting the field line, then this is called as a north pole. And if the other side is absorbing the same field, terminating at the other end, then that is called as a south pole. So that means the direction of this field line is from north pole to south pole. So like this, surrounding the magnet there will be many number of field lines, Now consider this region. In this region, so actually total how many lines are there? 3 lines are there. Each line is having some amount of force. If we combine all these lines of force in this region, then that is called as a magnetic flux. Magnetic flux is represented by phi and the unit is Weber. So consider this area, say this is S, through which there will be many number of lines are passing. In this case 3 lines are passing through the surface. So therefore the magnetic flux density is represented by B. It is defined as flux passing through this unit surface area. Phi is equal to B is equal to phi by S. So Weber per meter square, that is also called as a Tesla. Now consider a differential surface area ds within the S only. So through which the flux is d phi. Then the flux density for this differential surface area is B is equal to d phi by ds. So from this d phi is equal to B bar dot ds. So from this phi is equal to surface integration of B bar dot ds. So this is also one of the very important formula for solving the problem. Now let's see here the same thing. So magnetic flux means Total magnetic lines of force for a region is called as a magnetic flux. It is represented by phi and the unit is Weber. 1 Weber is equal to how many lines means 10 power 8 lines of force. Next, magnetic flux density is flux passing through unit surface area and it is represented by B bar and the unit is Tesla or Weber per meter square. Consider a differential surface area, that means this is represented by ds through which the flux is d phi. Then the flux density within this differential surface area is B bar is equal to d phi by ds. D phi is equal to B bar dot ds. Phi is equal to surface integration of B bar dot ds. Now you have one more definition that is called as a magnetic field intensity, that is also called as a magnetic field strength. Simply that is also called as a magnetic field, that is represented by h bar. So magnetic field intensity is nothing but for moving 1 Weber of force from one pole of the magnet. Now let's see the relation between the magnetic field intensity h bar and the electric field intensity, magnetic field intensity h bar and the magnetic flux density B bar. B bar is equal to mu into h bar, where mu is called as a permittivity of the medium. Mu is equal to mu naught into mu r, where mu naught is equal to 4 pi into 10 power 7. Mu naught is called absolute permeability. Mu r is called as a relative permeability. Next we are going to see about Biotsavarts law. So before seeing the Biotsavarts law, first we should see how the flux is present surrounding the conductor. So consider this is a conductor, right? So through which the current is I, When I current is flowing, then there will be a magnetic field surrounding the conductor. So the representation of magnetic field surrounding the conductor is based on the right hand thumb rule. Assume this is the conductor. Just to hold the conductor like this, this thumb indicates the current flowing through the conductor. The remaining 4 fingers that indicates the direction of the flux. If the current is flowing in this direction, the magnetic field direction surrounding the conductor is like this, which is in a completely closed path. Okay, this is the direction of magnetic field surrounding the conductor. Now suppose if you want to determine what is the magnetic field strength at this point, say this is a point P. This magnetic field strength is also called as a magnetic field intensity. So to determine the magnetic field intensity at the point P, first we need to consider the differential length. Differential length is represented by dl, through which the current is I. So because of this differential length, then there will be some magnetic field intensity at the point P, that is represented by dH bar. dH stands for differential electric field intensity. H stands for electric field intensity. Why it is dH means this is because of the differential length, not because of the whole length. To get the whole length, then we need to take the integration. So based on this concept, now we are analyzing this one. Suppose if the conductor, in this case conductor is perpendicular. If the conductor is not perpendicular, having some inclination, then we need to consider the angle between these two, the line joining the point P with respect to this dl, and this theta is also considered for the calculation of magnetic field intensity at the point P. So this is as per the Biotsavarts law. Now let's see here. Biotsavarts law states that the differential magnetic field intensity produced at a point P due to the differential current element IDL is directly proportional to the product of current and the differential element. Next, directly proportional to the sine of the angle between the two elements and the line joining the element to the point P, and inversely proportional to the square of the distance between the element and the point P. So this is the diagram here. This is a conductor. Conductor is not a perpendicular, it is some inclination. So consider the point P. At the point P, we need to determine the magnetic field intensity. First, initially, we will consider a differential length. Because of this, what is magnetic field strength at the point P? That is called as a dH. So through the dl current is I. So therefore, the overall term is represented as a IDL. And this conductor making some angle, that is theta, with respect to the line joining the point P from the ideal. Now mathematically dx is directly proportional to ideal sine theta divided by r square. Proportionality is replaced by constant where k is equal to 1 divided by 4 pi. So therefore dh is equal to ideal sine theta divided by 4 pi r square, which gives only magnitude only. If you want to determine the direction, then we need to write the vector form. So in vector form here, the magnetic field intensity at the point P, that means along this direction or along the radial direction. So the magnetic field intensity at the point P along the particular direction is dh is equal to ideal sine theta divided by 4 pi r square into ar bar. So here ideal sine theta ar can be replaced by one more term. Let's see here how this can be represented. Ideal is nothing but a, assume, and ar bar is nothing but b. Right? Next, sine theta is same sine theta only. As per the vector algebra, we know a bar dot b bar is ab cos theta. A bar cross b bar is ab sine theta. So this one looks like a same only, ab sine theta. So therefore this is replaced with ideal cross ar bar. So therefore ideal cross ar bar divided by 4 pi r square ampere per meter. Sometimes this ar bar, that is unit vector, is replaced by a vector component. We know that unit vector is vector divided by magnitude of the vector, that is r bar divided by magnitude of r bar. If you substitute here, then you will get ideal cross r bar divided by 4 pi r cube. So this is the magnetic field intensity at the point P due to this only differential length only. If you want to determine total field at the point P due to this entire length means, then we need to take the integration for this mathematical equation. If you take the integration of the mathematical for this equation, so h is equal to integral, and this integral is, it is a line integral of ideal cross r bar divided by 4 pi r cube, otherwise ideal cross ar bar divided by 4 pi r square. So in both ways we can write this total magnetic field intensity, that is h, that is magnetic field intensity h bar due to the entire length. H bar is equal to line integral of ideal cross ar bar divided by 4 pi r square ampere per meter. It is about the Biotsavarts law. Next we will see applications of Biotsavarts law. That is magnetic field intensity due to an infinite long straight. If we consider infinite long straight conductor, due to that what is the field produced at so and so point can be determined using Biotsavarts law. Here we are calling as a applications of Biotsavarts law. So that means the question is magnetic field intensity due to the infinite long straight conductor. To analyze this one here, first I will draw the diagram once again separately. Assume this is the infinite length conductor, that means plus infinity and minus infinity, through which the current is I. So once again consider this is a point P at which we need to determine what is the magnetic field intensity present at this point. That means when I current is flowing through this conductor, there will be a magnetic field surrounding that. If we take one point, say this is a point P, at this point how much magnetic field intensity is present, that we are going to determine using Biotsavarts law. Say this point P is located at a distance r from the origin point. So that means as per the coordinate system, it is x-axis, it is the y-axis, and this one is the z-axis. That means the conductor is placed along what axis? Z-axis. And consider the differential length as usual, right? In field theory, how to analyze means first we need to consider the differential elements. From that we need to obtain the remaining terms here. Say the differential length is dl. This differential length is located at a distance of z from the origin. Now because of this differential length, there is some magnetic field intensity at the point P. So therefore the distance between these two is represented by r bar. So this dl along the dz direction, so therefore dl is equal to dz az bar, right? And the point P is at a distance r from the conductor, that is represented by r bar. This one is z az bar. So therefore r bar is equal to, if you apply the KVL for this loop, r bar minus z az bar, that is nothing but this is dl as per this okay, and this is the point Z, okay. So that means Z into AZ bar. Next, this is a point P, so R into AR bar, and this is the radial distance that we need to determine. So this is R in this direction, this is in this direction. If we apply the KVL, right, that is Kirchhoff voltage law rule, the direction of the current flowing through that one across the loop, which gives the voltage equation. Here also the same thing, follow the same thing, then ultimately we need to get R bar is equal to R AR bar minus Z AZ bar. So this concept is used here for analyzing the magnetic field intensity H bar due to infinite long straight conductor. So initially this conductor is placed along the Z axis from minus infinity to plus infinity, through which the current is I. And we know dl is equal to dz az bar, idl is equal to I dz az bar. dl is equal to dz az bar. If you substitute, you will get this mathematical equation. Next, R bar is equal to, that is from point this point to this point, R AR bar minus Z AZ bar. Unit vector is AR bar is equal to vector divided by magnitude of the vector for this case. Now we are solving using Biotsavarts law, so therefore according to Biotsavarts law, dH bar is equal to ideal cross AR bar by 4 pi R square. Ideal cross AR bar is equal to, ideal here you got it, which is having only one term, that is AZ bar term. AR bar also you got it here, which is having two terms, AR bar as well as AZ bar. There is no A5 bar. So therefore ideal cross AR bar is equal to AR bar A5 by AZ bar. Why this is considered, why not AX AZ means the field is in the, that is magnetic field in the circular path, that means cylindrical coordinate system is considered. So AR bar, A5 bar, AZ bar. First we need to write ideal. Ideal is having only AZ bar only, that means there is no AR bar, there is no A5 bar, 0. Next, AR bar. AR bar is having two terms. One is AR bar term, another one is AZ bar. AR bar same as it is. A5 bar is 0. AZ bar is from this one is minus Z divided by square root of R square plus Z square. If you simplify this one using curly equations, then you will get finally IR dz divided by square root of R square plus Z square, A5 bar. Next, substitute that equation 5 in equation 4, then you will get dH bar is equal to this one. Now, this is the magnetic field intensity due to the differential length only. If you want to determine total magnetic field intensity at the point P due to the entire length is, take the integration on both sides. Then you will get H bar is equal to integration, the same term here. But in this case, integration limits are varying because the conductor is varying from minus infinity to plus infinity. So therefore, the limits are minus infinity to plus infinity. So later we need to modify this this limits. How to modify this limits means, if Z is equal to minus infinity, angle theta is equal to minus 5 by 2, and Z is equal to plus infinity means theta is equal to plus 5 by 2. Why means, so when this Z is tending to plus infinity, so when Z is tending to infinity, theta is equal to 90 degrees. Okay, so this theta is equal to 90 degrees. When Z is equal to minus this side, then that is minus 5 by 2. Minus 5 by 2. So Z is equal to R tan theta, dz is equal to R secant square theta. Substitute this entire things in this equation, then you will get H bar is equal to this. Once again further simplify, finally we will get H bar is equal to I divided by 2 pi R into A5 bar ampere per meter. We need to remember this formula. H bar is equal to I divided by 2 pi R A5 bar ampere per meter. Based on this, we need to solve the problems also. This is applications of Biotsavarts law. This applied to infinite long straight conductor to determine the magnetic field intensity H bar at any point in the considered region. Similarly, instead of infinite length, finite length, if we consider finite length means from this point to this point. Okay, so initially we determined with respect to differential length dl. Due to this dl, what is the field intensity at the point P? Next, the field intensity at the point P due to this entire length, because with respect to this point, this bottom line is making some angle, say theta 1. With respect to this point, this top point is making some angle, say that is theta 2. So but the angle theta is between the dl point to point P. So based on this theta 1 and theta 2, we are going to derive the expression, the magnetic field intensity at the point P due to this finite length. So the same sentence is exactly, everything is same as per the previous one. There is no change at all. So including this r vector also, right, as it is same only. Only one thing is limits will change. In this case, in the previous case, minus infinity to plus infinity. In this case, theta 1 to theta 2. Everything is same only, right? So finally, h bar is equal to this. Okay, z is equal to r tan theta dz. Z is equal to z1, z is equal to z2. Z1 is equal to, in this case, theta 1, z2 is equal to theta 2. That we need to replace, because the limits initially from z1 to z2. What is z1 is theta 1. What is z2 means theta 2 from the diagram. So finally, you will get the mathematical expression h is equal to I divided by 4 pi r, then sin theta 2 minus sin theta 1 a phi bar. This is a mathematical equation for the magnetic field intensity for finite length. The previous one is infinite length. Okay. Next we are going to see about Amperes circuital law. So to discuss Amperes circuital law, one simple concept in this case is, first consider this is one differential length dl. Assume the magnetic field intensity or magnetic field strength for this one is h. Similarly, one more differential length h, one more differential length dl. The magnetic field strength is h. One more differential length h, one more differential length h, one more differential length h, and one more differential length h. If we combine all this, because which forms a closed path, if we combine all this, that is nothing but integration. H bar dot dl is equal to current flowing through this, which is the statement of the Biotsavarts law. Because if you want to add all this small differential length, right, is nothing but integration. Integration h bar dot dl is equal to, because which forms a closed path. When magnetic field is present for a closed path, then there will be a current flowing through that. That is, current is nothing but I. See the statement of Amperes circuital law. Amperes circuital law states that the line integral of magnetic field intensity h bar around a closed path is exactly equal to the direct current enclosed by that path. Mathematically, line integral of h bar dot dl is equal to I. Let's see the proof for this one. The proof is also same, right? Once again, we need to consider, okay, we need to consider the same thing as per the analysis. First, small differential length, combine all that one, will form a circle, and so proof is, consider a current carrying conductor placed along the z-axis by a magnetic field due to a current I ampere. So let R be the radius of the closed path surrounding the conductor. So consider a differential length dl at point P, right? So this is moving along this closed path direction, means a phi bar direction. So dl is equal to r d phi a phi bar. According to Biotsavarts law, h bar due to the long straight conductor is this one. For this conductor, h bar is equal to this. But h bar dot dl is equal to this one. This dl is this, h bar is this. Take the dot product. Finally, So take the integration on both sides. Integration of h bar dot dl is equal to integration of this. So if you take the integration for this, the limits of d phi varies from 0 to 2 pi. Finally, line integral of h bar dot dl is equal to current I only. That means for a closed line, for a closed path, the line integral of magnetic field intensity is equal to the direct current I. Next, point form of Ampere circuit law. So from the Ampere circuit law, we know line integral of h bar dot dl is equal to I from the Stokes theorem. So later we'll discuss about this. So line integral of h bar dot dl is equal to surface integration of del cross h bar dot ds, and we know the current I is equal to j bar dot ds. So then using this one here, so j bar dot ds, I is equal to this. So but I is equal to this. So finally, the surface integration of j bar dot ds is equal to surface integration of del cross h bar dot. This del cross h bar can be made equal to this. This is nothing but I is nothing but this. Finally, we'll get this is surface integration. This is also surface integration. So both can be made equal. This is ds. This is also ds. Finally, j bar is equal to del cross h bar. That means j bar is called as a current density. Current density is equal to curl of a magnetic field intensity. So current density J is equal to the curl of magnetic field intensity. This is called the point form of the Ampere's circuit law and one of the Maxwell's equations for magnetostatics. Now applications of Ampere's circuit law. We'll see magnetic field intensity is due to infinite long straight conductor using the Ampere's circuit law, right? So we need to consider once again conductor, infinite long straight conductor placed along the z-axis, minus infinity to plus infinity. Once again, right, through which the current is I, which producing the magnetic field surround. Now let's see here. This is the conductor placed along the z-axis from minus infinity to plus infinity, through which the current I. So when the I current is flowing through the conductor, there will be a magnetic field surrounding this conductor. At one particular point, if you want to determine how much field is present, say consider the point P, and which is at a radial distance r from the conductor. Okay. Now see here the points which is placed along the z-axis through which the current I. Consider a closed path of radius r which encloses the conductor. Consider a point P at a distance r from the conductor at which the h bar, that is magnetic field intensity, is to be calculated. Next, consider a differential length dl which is moving along the same d phi direction. So dl is equal to r d phi a phi bar and h bar is equal to h phi a phi bar. H bar dot dl is equal to this, finally h phi r d phi. So according to Ampere's law is equal to, because in this case we need to use Ampere's law. Why means the question is itself is application of Ampere circuit law. We need to use the Ampere circuit law formula only to calculate the magnetic field intensity at the point P. Okay, so according to Ampere circuit law is equal to line integral of h bar dot dl. Now substitute h bar dot dl from this, then h phi d phi, then the limits varies from 0 to 2 pi only. Finally we will get I is equal to 2 pi r h phi. H phi is equal to I divided by 2 pi r. So but h is equal to h phi into a phi bar. So multiply this term with a phi.